Okay, time to get started. Let's see. It looks like we're recording. Fingers crossed. Weird audio stuff this morning. Okay, so a quick comment on the attendance quiz. I made this attendance quiz myself on Canvas. I haven't done that for a couple of weeks, and there were little details, and I didn't get it right the first time. I think everything should be working okay with the quiz, but anyway, don't forget, that disappears in a minute and a half, so make sure to do that Canvas attendance quiz immediately. Okay, so back to it. So this is where we ended last time. We were talking about this theorem called the implicit function theorem, the big idea of which is that you can address the question of if you have an equation involving several variables. Notice, all of those variables are input variables. They're not necessarily functions of the other variables. I mean, maybe they are, but maybe they're not, right? And we saw some examples starting off here that, for example, at a point like this, no matter how locally you, no matter how narrowly and myopically you restrict your attention to just even so much as a teeny little part of that curve, you cannot claim in any reasonable sense that y is a function of x. Near that point is absolute nonsense. And so it's not that the derivative fails to exist in routine ways as derivatives fail to exist sometimes for functions. It's that there is no function to even talk about the derivative of in the first place. Right? So it's really, really deep problem that we're trying to worry about. So anyway, our theorem that we came to last time is that if one of these variables, whichever one it might be, I don't know, right? But if you want to view one of those variables as being a function of the other variables, the big test, the way you do this is you look at the partial derivative with respect to that variable, and if that partial derivative is non-zero, then there's no problem. Right? Nice and simple little test. Partial derivatives, world's easiest derivatives to take. Just punch it up and evaluate it and see what it is. And if you're non-zero, no problem. Don't even worry about this issue at that point. Okay. So let's see an example of this in action. So here is, in fact, such a scenario where I have an equation involving three variables. By the way, do notice the variables here in this equation are not called the same thing as they were in the theorem. In the theorem, the variables were called x1 through xn. In this example, they're called something else. World's most routine little opportunity for confusion, right? This happens all the time. Any application you're doing of math, the variables are going to be called whatever's convenient for that circumstance. So this is not weird. Right? We're going to ask exactly the question that our theorem is made to answer. Namely, I'm going to ask, is x locally a function of the other variables? And reminder, our rule here, whichever of these input variables that you want to view locally as being a function, we're going to take the partial with respect to that variable. All right? It's very, very explicit. And so, cool. Here's our capital F. This is the thing whose level set we're looking at. All right? That's our capital F, in other words. So that function, you take the partial with respect to whichever variable you want to view as being a function of the others, per the rule. Again, per the implicit function theorem. And, you punch it up. It's not a hard calculation. This partial derivative computed by that, which, you can plug in the point in question, and that partial derivative at that point ends up being not zero. So not zero, so no problem. And otherwise said as, yes, you can view x locally as being a function of y and z. Now, what does that look like? This is some sort of a surface, right? If you look at that that green equation we started with, does it mean that I know what that surface looks like? Oh, gosh, no. Right? Not even close. I have not the slightest what that looks like. And that's the power of the implicit function theorem. I don't need to know what it looks like. All I need to know to the question at hand of can I view x as being a function is that partial evaluated at the point we're interested in, non-zero, boom, game over. All right, very, very wonderful theorem. All righty, now that naturally brings up a question. So we got a new function, right? We've just confirmed that yes, x is a function of y and z. How would I compute the partial of x with respect to either y or z? Okay. So this is another separate question we have to worry about, and we're going to deal with this in a different way. I'm going to wave my hands at this first answer that I'm going to show you. You don't need to look at this if you don't want to. The reason I have this in here is because this is a way to answer that question that doesn't involve little math crimes where in fact, because I'm about to commit a math crime momentarily, I'm going to break one of my own rules about how to use the chain rule momentarily. But this does not break my rule. This is a right and proper. You can see I've added certain variables. You remember we've done that before. When you have a diagram that's not really, you're not really allowed to do that kind of thing. It's not a composition of functions. You can very often add new variables and make it legit. And you'll notice here, this is fine, right? I clearly have a composition of functions, and so everything goes through fine. And the only problem with this solution is it's a little heavy-handed and a little scary looking. So let me show you what I think is the, streamlined for this particular narrow purpose. I think really the better, more intuitively satisfying way to think about it. Notice that my diagram breaks my rule. This is what's going on here? I mean, that's strange looking, right? That I have an arrow that goes vertically, maybe. So this is a intuitive purposes only explanation, but I think this does work very nicely. First, let's recognize how this kind of represents what we're talking about. We have some expression of several variables called f, and of course the whole point is that we're setting this equal to a constant, so let's not forget that's a constant. And as we've just discussed, we've got a condition whereby I can view xi as being a function of the other input variables, not including itself, of course. So. And with that understanding, we are going to ask, okay, forget about f for the moment, understanding xi as being a function of all these other variables, what if I want to take the partial derivative with respect to xj? In other words, what if I want to hold all of the other variables constant, let only xj change, and I want to know how much xi is going to change as a result of that, right? So this is kind of a sketching out of the scenario that we're looking at here. So the way we answer this question is actually pretty straightforward. We're just going to write down the chain rule. You can see we've got a bunch of stuff that's constant, and so there's really only two paths that we need to worry about. For one thing, changes in xj will make a direct contribution to changes in this expression f. On the other hand, there's this other path, sort of a two-step path, orange followed by dark blue, that also will make a contribution to how much capital F is going to be changing. Right now, which wasn't our question, right? Our question is, how much does xi change? I want to compute that orange partial derivative. That's my goal. And again, as we often do in this class, and as you'll often do in other math classes, we're going to find an answer to a question by asking a different question in which what we're interested in shows up. and then we'll kind of reverse engineer what we're actually looking for. So, so what we have here is a computation of how much f changes. But wait a minute. The whole point of this exercise is that we were looking at a level set of f. F is not allowed to change. So these two different paths leading to two different contributions to the change in f, well, they have to add up to no change in f because f is not allowed to change. Okay. All right. And so having written that down, got this equation here. And let's see, we were interested in figuring out that partial derivative, which is right there in our equation, which makes it easy to solve for, and bam, we have ourselves an answer. So, I think this is a, now again, math crime, right? Fully confessed. Don't try this at home, right? I'm doing this in a way, in a situation where I know exactly what could possibly go wrong. And again, here's the legit, fair version if you're interested. But this is a math crime that doesn't lead to any problems. And I ask you to take my word for that. Okay. So a couple of things to say about this answer. First of all, how convenient. Right, we're interested in computing a certain partial derivative. I don't even have a formula for xi. Right, the whole point to this is that I don't apparently have the ability to solve for xi. Otherwise, I just would and take the derivative as usual. Even without knowing the formula for xi, I've got a formula for how to compute its partial. So handy dandy. Next thing to say about it.